I think we can start. I just change. Okay. So, welcome everybody. The speaker today is Mauro Pieroni, who did his PhD in Paris. Yes. Then he moved to then to the Imperial College, and now he is at CERN. And today he will talk about measuring the
Stochastic Gravitational Wave background
with PPA. So Mauro, I leave you the floor, and I will give you 5 minutes before the end.
Okay. Thank you very much for the introduction and for inviting me here to present some of my work. So this is an outline of what I'm going to discuss today. I will start with a very broad introduction to the topic. Probably I will also mention things which are known to everybody here, but okay. Then I'll move on how to measure gravitational waves with Pulsar Timing Array experiments. I'll tell you about this thing we're working on right now with some collaborators about a new methodology for getting forecasts, which speeds up the machinery quite a lot. And then I'll move to conclusions and how to look. I suppose most of the people in the room know what gravitational waves are. So I'll skip that. The important thing is, which probably is less known to people, is that there are two main classes of signals. There are individual signals, which are the signals we've seen this far with interferometers. From now on, LIGO, Virgo, Kagra is LBK. This is the kind of signal you see. So something which has some clear morphology in time and frequency. There is coherency, and typically these kind of signals are localized in the space, in the sky. The other class of signals, which is going to be the topic of the rest of my talk, is stochastic backgrounds. These are signals which are stochastic. So basically, they have no time coherency. They behave more or less like noise. And here you have some example of what this would look like. These might come from astro. So if you have the superposition of many weak signals which you cannot resolve individually, in the end you will end up getting something like this. Or otherwise, there could be early, processes in the early universe which might generate these kind of signals. Another big difference is that these are typically diffuse signal, meaning they come from the whole sky and not just from some specific direction. This plot shows the different detectors we have now and in the future. Colorful lines are current detectors. Black lines are future detectors. This is frequency. This is characteristic strain, which is basically the sensitivity of your detector. And this is compared to several possible sources in colorful bands. Now, to the very right here, you have Earth-based detectors, LDK, which are sensitive to roughly the Earth up to few thousand Earths. Then if you want to go to lower frequencies, basically you have to avoid the wall due to seismic noise. And for doing that, you throw your experiment in space. You make it huge. That's what you do with LISA, for example. And LISA is going to be, and these kind of detectors are typically sensitive to a frequency band which is about 10 to the minus 3 Hertz, roughly. And then if you're going to go to even lower frequencies, you need your detector to be really huge and actually parsec scales. And the way to do it is basically monitoring pulsars. And I will explain the idea of how this works in a moment. This plot, on the other hand, is more concerning signals. What are the different possibilities with respect for cosmological signals? Here I'm comparing, again, frequency versus the intensity of the signal. I'm comparing the different possibilities with some detectors, including CMB experiments down here. These, again, are Pulsar Timing Arrays, LISA, and here you see LBK detectors and also Einstein telescope. The different curves, on the other hand, are the possible signals you might have, some examples of those at least. In the next few slides, I'm going to explain a bit better what inflation, cosmic string, and phase transitions are. Here, I'll just mention briefly what this curve is, which is, here with an abuse of notation is called PBH, but in reality, this is scalar-induced gravitational waves, meaning if you have very strong scalar perturbations, they generate tensor at second order. And typically, you need the scalar spectrum to be very peaked, meaning also the tensor spectrum is peaked. Let me explain a bit better what the other things are. Let me start with inflation. So the idea is you need some early epoch of accelerated expansion of the universe. So in the minimal realization, you just take a single scalar field minimally coupled to gravity with this action. What you want then is to check what the Hubble rate is. Here, A is the scale factor. What you want is A to grow exponentially, meaning you want H to be constant. And you can see from these equations, which are Einstein equations, that you need phi dot to be basically 0, and in particular phi dot to be much smaller than v in order to have h which is constant. In field space, what you need is basically some configuration like here. So you need your field to be slowly evolving in a region where the potential is basically flat. And then at some point you have the field to accelerate in order to repopulate the universe. This is the background scenario. Then what you have on top of these are perturbations, and what happens with perturbations is basically shown here. You have scales which initially are small, so you have these perturbations which are generated inside of the, at very small scales, and they are quantum. They are stretched by the expansion. They become larger than the Hubble patch at the time. They stop evolving, they freeze out, and at later times they really become causal and they start affecting what you see in your universe. This is basically the main idea. Now, if you look at the signal you get out of inflation in the minimalization is this dashed gray line, so something you cannot really see. What you need is something which is beyond the minimal scenario. For example, this you can achieve coupling your improton to other particles. There are many ways to do this. I'm not going to discuss this in detail, but I'm just going to show you that this line here is what you get if you have this axion inflation model where you basically assume your improton to be an axion and you couple it to some gauge fields through this non-minimal coupling, this Chern-Simon term. If you want more details on this, I can tell you later. Cosmic strings, the idea on the other hand is assume you have some spontaneous symmetry breaking in the early universe. What you need is your vacuum manifold to have some non-trivial structure. So this left image here is field space. This is physical space. What you want is assume your phase transition occurs. You want this to be sufficiently fast so that if you take points which are sufficiently far away from one another, and in particular farther away from than an Hubble distance at the time, that they become non-causal with one another. So in that case, you can pick values which are random from one another. So basically, you pick random points in this circle here. If you end up picking points which create a full loop around your U1, what happens in physical space is you create this loop here, and you interpret that as the loop being pursed by a string. If you just study how this occurs, generically it might happen if you have this kind of scenario. So what you're left with is your box, your universe filled with these strings, long strings which are going around. Evolution make these strings intersect with one another. So they chop down from long strings into loops. Loops emit a lot of energy in gravitational waves. And in the end, you end up having a background which is with this shape, which has this shape. So you have some kind of bump here, and then it gets flat. What controls the height and the position of this peak is basically the energy at which the spontaneous symmetry breaking occurs. The higher the energy, the higher goes the signal, the more is the intensity, and it moves to the left. More or less, this is what this G and mu parameter is controlling. And this is comparing my spectrum to some experiments. These are our NPAs. The last mechanism discussing here is first order phase transitions. The idea is you have some effective potential, which changes with the temperature. Now, let's assume I start here. The temperature goes down, the potential changes. If I develop some false minimum here, so that the field gets stuck in there, what happens is that eventually, when the field tries to tunnel down to the real minimum, this is what happens in the physical space. So basically, you're left with your universe, which is a sea of false vacuum, where bubbles of two vacuum start to nucleate. These bubbles become bigger and bigger. They go to collide with one another, and when this happens, you generate a lot of gravitational waves. And also after that, you're left with a fluid which is not symmetric at all. So it's trying to relax in some way, and again, it's emitting a lot of gravitational waves. The spectrum which you expect is something which would be some of this shape. So you have some kind of peak. The temperature at which the phase transition occurs is controlling the position of the peak. And then depending on how fast the phase transition is, you can have more or less energy or other changes in the shape, which I'm not going to discuss in detail, but if you want, I can tell you later. What this plot is showing is basically which part of the parameter space we can probe with gravitational wave detectors. This is the temperature, and this parameter basically controls how fast the phase transition is, let's say. One thing which is interesting, I think, is that, and is shown in this plot in a not super transparent way, is what you can see here is this gray band is the part of the parameter space which you can access with colliders. And these curves here, the colorful curves, correspond to different values of the SNR for signals at LISA. So basically, the idea is points which are not in the gray area corresponds to models which you cannot see easily or not at all with colliders. Points, on the other hand, points which fall inside of these curves, maybe you might probe with LISA. So in some scenarios where you end up having first transitions, which can generate strong stochastic backgrounds, it's possible that these signals give you information on physics beyond the standard model, which you cannot access with colliders. So this is important for people who do particle physics, I think. Now, I've talked about signals. Let me explain a bit what the status is with PDAs. So the idea, first of all, is how do we measure gravitational waves with PDAs? Pulsars are very precise clocks. So the idea is if I monitor the pulse I receive for sufficiently long times, and I see deviations in what I expect the pulse to be, I might interpret that the gravitational wave. Now, if I try to do that with a single pulsar, I'm not going to get anything because things are a mess. So what I need to do is to monitor many pulsars and look for correlations, which we also, and cross-correlating, I'm also killing the different noise contributions. The moment when I started to get interested in this was basically when this paper came out a few years ago. So these two plots are from the nanograph paper in 2020, 2019. What these are showing are this frequency, and this is basically the intensity of the residual they are measuring. So you can see that at the time, they basically had these 2 points where there was something, and the rest, which is basically noise here. So they started to see some extra power in the data. The problem is that if you start to look at correlations in the sky, and this is what this plot is showing, the x-axis is the angular separations within your pulsar, y-axis is the correlation you would expect in your signal. So if this signal is really coming from gravitational waves, you expect it to be aligned along the blue curve, which is Ellington Downs, and I'm going to explain this in a moment. What that is in a moment. You can see that the black data are not really aligning along that. So there was something at the time. It was not really clear what that was. Things improved with the last release last year in June, July. Here I'm showing the plots coming from all the different collaborations, and you can see that now all the collaboration are seeing this excess at low frequencies, and at the same time they start seeing something also for what concerns the angular correlation. So we start building up some evidence for this detection, but you cannot still claim phi sigma for the moment. What's going on at the moment is trying to combine the different data sets. This is something that is done, this effort is done by the International Pulsar Timing Array collaboration, IPTA. What they're trying to do is to combine the data coming from all the different pulsars. There are pulsars which are in common, pulsars that are monitored just by one collaboration, pulsars that are monitored by a couple of those. What they're trying to do is to take all of them and assemble the data so as to improve your constraints. This plot down here to the right is showing what the constraints on your spectrum would be if you take one of the data sets or if you combine them all. This combination, though, is not done in the proper way, but okay, for the moment, it's giving you an idea of how things would improve. Doing this properly is still something which is ongoing, but at least gives an idea of the fact that things shrink as you would expect them to. Okay, this is all for the introduction. So before I enter into data or whatever, are there any questions? Last chance. Okay. Data. So here I'm basically trying to explain you how I would model my data in the following. So my data are assumed to be just a combination of signal and noise, as I'm writing here. Now the noise is something which is stochastic, so it has no mean, it's just some variance. Signal, depending on whether this is coming from individual sources or stochastic backgrounds, it might or might not have some mean. Stochastic background has the same properties as noise, so all the information is contained in the variance. So the mean doesn't contain any information. So if I want to extract information from a data, what I should look at is BD here, which, assuming signal and noise to be uncorrelated, I can expand as signal and noise. So signal is the power spectrum of the signal coming from the sky, modulated by the response function, this R here, automatically. And then NN is just the noise of my detector. What they can do, and this is what is typically done in LBK papers, is to factor the response out and define the strain here. So the strain is basically the noise divided by the response of the experiment. So it's a curve which you can directly compare with the with the power spectrum you're getting to have an idea of whether the signal will be visible or not with your detector. finally, since at least I am interested in doing cosmology, what I do is to convert this stuff in omega units just by rescaling by some powers of F and by the total energy in the universe here. And the same thing you can do for the noise. So when you see sensitivity in omega units, keep in mind that this is just the strain rescaled by this quantity. Nothing more than that. Data, what do the data we get contain? So basically what we are observing are pulses coming to us every few milliseconds. And these pulses we observe at different frequencies. So here what this plot is showing is what the profile of the pulse is at different frequencies. And this is what you get if you rescale all of them so that they have all the same amplitude. So when you normalize them all. Now the idea is that if you look at a single pulse, this is very difficult to, I mean, you cannot really say much. What you want to do is to monitor many of those over very long times so that you can go to very low frequencies. And then you can start saying something. Just to give you an idea, a year roughly is the inverse of a year. The frequency corresponding to a year is basically this. So when you want to go to 10 to the minus 9, you basically need at least 3 years schematically. Now, how do I interpret what I get in my data? So as I said, signal plus noise. The signal is a real signal times a response. Let me try to explain what the response is. So the signal I'm looking for is the time shift induced by a gravitational wave passing by on the signal coming from me to me from a pulsar. So this object is just a time shifter. This P hat is the direction going from me to the pulsar. This H is the gravitational wave, and this S is the affine parameter along the line connecting me to the pulsar. So basically, you just have to do this integral. The way to do it is you plug in some Fourier expansion for H in plane waves. What you learn is that this delta T becomes just H. This H here is now the Fourier coefficient. AB here is the polarization tensor for my two modes for the gravitational wave. And this R is the linear response. As I told you, the information is not contained in D, but in DD. So what you want to do is to compute delta T. And this stuff now contains something that is meaningful. In particular, if you compute your integral plugging back this stuff, so I'm assuming my spectrum to be isotropic and I'm not breaking Lorentz, doing nothing funny. If you plug that back into your equation here, what you get is, this expression. So all the angular information is contained in the response. The spectrum contains some power at different frequencies, and that's all I have. So this object, this R here, is basically the response integrated over all the angular direction from which my gravitational wave might come. So this object, this R, contains two dependencies. There is one part which is frequency dependent, which is basically telling you that depending on the size of your detector, you might or might not see gravitational waves at those frequencies. And then there is another part which is containing the information on what you are doing concerning correlations. So what this plot is showing is, assume I take a pulsar here, another pulsar here, how correlated would the signal be? So basically this thing is telling you, depending on the angular separation between your pulsars, what do you expect the correlation to be in your signal? Full stop. That's what it's telling you. Now, concerning noise, I'm not going to discuss all these things in detail. What you have to, I mean, the only important thing is that different noise might have different properties. Some noise will be white, some noise will be chromatic, some noise will be uncorrelated spatially, some noise will have spatial correlation. Whenever you write down your noise matrix, you would have to expand it in such a way that you keep track of each one of these components properly. That's all I wanted to say. The only important thing is that, as far as I know, none of these components, even if they might have some angular correlations, you won't expect those to behave as a quadrupole. I mean, they might behave as scalars. For example, if you're making some mistake in monitoring where your pulsars are in the sky, it's going to affect all of them overall simultaneously. But none of these things are expected to have the same angular structure as gravitational waves. That is the key. Okay, to speed up a lot. Let me briefly mention how the standard thing is done, the standard analysis. What you do is to take the residuals, so pulses minus the best model you have for those, and you try to express, I mean, to build some model to explain what that is. And basically you have something which is some additional residual on top of your model, Fourier coefficients which are mapped onto the time residuals by some Fourier matrix, and then noise. What you do is to write down a Gaussian likelihood for your noise. You try to marginalize over these other two contributions, and that's what you're left with. Something very simple. Now, what you can do is to use these, just explaining, just choosing what the properties of your noise are, what the signal are, and you can try to use that to compare to data. This is what was done already, and there are already papers coming from the different collaborations putting constraints on the different fundamental physics models. I have to be fast on this because I'm running out of time. And what we did, for example, with Matteo and Fabio, is to check how much constraints would improve if you try to cross-correlate with our probe, in particular with spectral distortions, but I won't have time to discuss this in detail. The thing I want to mention, though, is some work we're doing right now with other people, which is all the machinery described works, but it's low. Is it possible to speed up? The idea is the following. Let me just say I take the full data, which are a lot of data with a lot of structure. Let me just Fourier transform those. Let me just build the likelihood for my Fourier transform data. This likelihood is just this stuff, something very simple. And what I'm doing is to express here my noise and here my signal, which is again some fundamental signal modulated by the response. With this, what I can do is also to build some Fisher formalism, which is second derivative of the likelihood, basically, evaluating in the injection. That's it. Now, let me try to see if this thing is giving something which is compatible with what I get doing the full analysis. Let me assume my signal to be just some power law signal. So something here, super simple, just an amplitude and a tilt. And let's see what happens if I compare that to real data. So the left plot is, so the red curve you see there is the constraint on this particular template coming from current data, so present data. Green is what I get with my approach. So they're matching more or less, but not exactly. And the reason is because real data are not perfectly Gaussian. I mean, the evidence for what I'm measuring is not that strong. So it's normal that the things are not matching perfectly. The other two plots, on the other hand, are showing what I get if I run current simulations to generate future observations using the, up-to-date machinery to generate something which is, compatible with what we would expect to measure. And then if I analyze it with the full data analysis pipeline, that's what I get here for something like current EPTA by 20 years and SKA. That's what I'm showing in red. And in green is what I get with my approach. So again, things match pretty well, even if this stuff was expected not to work at all, apparently. And there are some reasons for that, but I'm not going to discuss those. If you want, I can tell you later. Let me also try to see if this works if I do something a bit more complicated. So not just a single power law, but a combination of signals. Does this work? Does this still work? The answer is yes again. Red is again what I get with simulations, and green is with my approach. Just want to mention that the full analysis takes order 1 day on cluster, green seconds on my laptop. So there is a great improvement in doing this. I mean, you're losing some information, but depending on what you're aiming for, might be worth. One very last thing, and then I conclude because I'm super late, I think. Okay. So what we tested is, to understand if it's an accident or if it really makes sense that this works, is how do results scale if I change, first of all, the number of pulsars. Left plot is showing you how the SNR increases if I increase the number of pulsars, and it does what I would have expected it to do. And left plot is showing you how the errors on my two parameters, amplitude and tilt, change if I increase the number of pulsars, and this scales as I would have expected it to scale. These other two plots show how the SNR and the error scale if rather than changing the number of pulsars, they change the observation time. Here you see two regimes, unlike the first plot. These two regimes are the second part, where it scales like with square root of t, and here 1 over square root of t, is what you get in the signal dominated regime. The left part is noise dominated. So the reason why I get the scaling is because if I look at this equation, you see you have this integral here. So this t in front is what would give you the square root of t when you are in the high end part. When you are in the weak part, what you are changing is this extreme of the integral. So when you go to lower frequencies, to longer times, you can access lower frequencies. So there is a regime where changing the extreme of your integration affects a lot your results. And this part is actually model independent. It changes if I change the shape of my spectrum, but I can predict it given the template. And then at large, I mean, when I enter the high scenario regime, things do what I expect to be doing. Okay, that's everything I wanted to say. Just a recap, I think I explained more or less how present techniques work. They are fine. You can use them to put constraints on fundamental physics models. But I mean, they are not super fast. Being a theorist, I want answers in seconds because I want to check if my model is going to work and is going to get me my Nobel Prize. So I cannot wait for a class to give me the answer. So what we try to do is to see if it's possible to do this with fast techniques which preserve the information. And it seems like all this works. It's important, though, not to forget that at the moment we've only done something, I mean, approximate is before claiming this is really working, I would want to go through some more thorough validation of what we did. Future perspectives, testing these on many different signals, which, I mean, I discussed some of the possibilities. It would be nice to try to see what you can do if you systematically scan the parameter space of all these models. And with these, you can do it easily. Another thing which I think is important is trying to understand better how the different noise components would affect the measurement. At the moment, I just put all of that in, but I've not tried to see what happens if I degrade some parts. That is something I can do easily, and it's very complicated to do with the standard approach. Finally, here I've not discussed trying to reconstruct the Ellings and downs, which is something which is very important if you want to claim that your signal is really gravitational waves. That is something we have to include, and yeah, we're working on that right now. And that's all. Thank you very much for your attention.
I might add one.
Yes, please.
So, generally speaking, like I was puzzled by the when you were showing the timing of the pulsar that you would need. So it's how many pulsar have this behavior, like very low?
You mean what? So which?
So there was no, like at the beginning of the.
You mean?
So when you were showing the.
We get there.
Sorry.
You mean this? No.
No.
Not the Ellings and downs.
No. So basically,
the pulsar.
Exactly.
Okay.
So like. You were pointing out that you will need like at least 3 years to collect the data you would need to perform your analysis. But I couldn't really understand why like you are aiming to this very like long time for
2 reasons. Mostly I want to kill noise, and high frequencies noise is huge. So if you look at this plot, for example, these guys up here. So these are in omega units. So if you want to go back to strain, you have to divide by f cubed. So build it back. That part that goes up here, this stuff is white noise. So in this part, you see nothing. Here is where you see the signal. So the reason why I want to go to very low frequencies is because at larger frequencies, the noise is huge. So I need to really enter that regime or even these plots, for example. So you see, this is where I can kill the noise. This part is where the noise is dominating.
Okay, and the number of and this is the number of objects that like of pulsars in general.
This is what I get when I combine all of them.
Okay.
So the point is, I would need so I can do the analysis with less, I mean, with shorter observation time. But at that point, I would need a much better understanding of the noise to be able to see the signal coming out of it. The point is I have noise and signal there. If the signal is not sufficiently strong, the noise will dominate. So either I manage to make the noise much, much smaller, and then I can see a signal which is weaker, or otherwise, since the noise is flat and the signal is expected to go up here, if I manage to go to lower frequencies, eventually the signal will win.
Okay.
So that's the idea. So you need some part, okay. You need to monitor those for very long times, because if you don't have very long times, it's just a matter of doing Fourier, no? To go to small frequencies, you need long times. So that's why you need long time to get there.
Okay. Thank you. Other question?
Crystal clear.
So if not, let's start the speaker again. Let me just see if there are questions from Pieroni. No, okay, so it's done.
Yeah, I have a question.
I couldn't see the, okay.
And I think it was a yes when we were asking if they were hearing us.
No, there is
Okay. No, because I saw that it was 14.
Can you hear me?
yes.
Briefly.
Okay, thank you. Yeah, I was wondering if you could talk a little bit more about the cosmological background, because that was one of the first results you mentioned, but you went really fast. So could you talk about this a bit more?
This plot here.
Yeah, constraints on new physics, yes.
Yeah, I mean, okay, let me remute here, or I would hear myself. So what this is showing basically is so right plot is the evidence for some models using the interpretation as astrophysical signal imposing only gravitational wave emission, isolated systems, whatever. But bias factor being large means your model is favored compared to the reference model. So you can see that there are some models that apparently are strongly favored compared to interpreting these as just astro signal. In my opinion, all this needs way more testing to be able to make any statements. Because if I look at this plot here, on the other hand, what you see is that basically the beans that are bringing information are these 4 or 5 beans here, right? All the others, you are basically dominated by white noise. So, I mean, you can make statements on this, but I'd say for the moment, it's still a kind of weak statement. So if you want to tell you about the different models, how well they perform compared to Astro, but before making any statements on saying we saw new physics, I'd first try to make sure that we understand everything which is in the data. And also, yeah, I would wait for more evidence. That's my take on this. I don't know if this answers your question.
Okay, thanks.
Any other questions? If not, this time we can have the speaker.